Broadly speaking, fluid flows can be classified into two different categories. Laminar flow, in which parcels of fluid move smoothly against each other and continuously move without mixing laterally, or turbulent flow, in which swirling, whirling motions mix material and mix fluid from one part of the flow to the other. I'm going to illustrate these two. So on the left-hand side, I'll write laminar. And on the right-hand side, I'll write turbulent. And so if we draw some streamlines, and these streamlines are lines showing the velocity path taken by the flow, the laminar flow is just going to look something like this, with a few streamlines going in next to each other. And even if that laminar flow is forced to move through some sort of conduit, so I'll just create some sort of like pipe here, and maybe even if the pipe has like this big constriction over there, or tiny constriction, I guess that's the way that you describe that, right? The flow lines will still stay parallel to each other. The flow lines will still stay parallel to each other. There we go. And they will not cross. Pretend that's slightly more perfect than I drew it. Not that little oopsie in the middle. Meanwhile, turbulent flows are known for this kind of swirling and churning, and so you can imagine a river if you've seen these boils of water coming out of the surface. If you haven't seen a river, you can imagine a pot of boiling water. That's a good example of turbulent flow. And so if we draw, let's just draw kind of a mock-up riverbed. So I'm just going to draw, I'll use black, draw this river channel, and so there's going to be a bed down here. And then I'll draw a free water surface up at the top. And we denote the water surface with this triangle and these two lines. I don't know why that's done, but that's always done for the free water surface, and so that's just, a symbol that, engineers and scientists who work with these sorts of systems know what that means. And so this is going to be water surface. All right, excellent. So then, inside this flow, we're going to have, some like little eddies like this, and maybe over here, and maybe we'll have some medium-sized eddies like this one coming up here, or maybe like this one going around like so. And notice that I'm drawing these eddies such that there's always continuity of water flow between them, right? We wouldn't have an eddy flowing backwards this way, because that would create shear against this, and those two forces would start to interact and possibly cancel each other out. So these eddies are always existing in pairs and interacting with one another in the flow around them. And we might even have some very large eddies, so you can even imagine something like the gigantic eddy like this, that's bringing parcels of water all the way from the bed up into the middle of the flow, and then eventually into the surface. And so what that's doing is actually causing these water parcels to be able to experience conditions at all parts of the water column. And that's not the case in laminar flow, where one parcel of water starts here and trucks along to here and continues along to here, right? It stays in the exact same position. So these parcels of water are actually able to mix up and down and move. And that's one key characteristic of turbulent flows. So why is flow in some places laminar, and why is it turbulent in other places? And the reason behind that is this concept called viscosity. So the viscosity, gotta find a good underlying color. Let's do blue for water. So in laminar flow, viscosity, which is like the stickiness of the fluid, or more formally, it's its resistance to shear, or resistance to straining in general, is the characteristic that would then cause it to want to dampen out any sort of inertia, right? So if you can imagine trying to like punch through like a cubic meter vat of molasses, your fist is going to hit it, and it's going to slow down and slow down and slow down. You won't be able to just swing through like you would in air. And so in laminar flow, this viscosity is going to be dominant over inertia. And so, on the other hand, in flows that are turbulent, inertia will be dominant over viscosity. And what that means is that instead of dampening down, things can swing around and fly wherever they will. And we have a quantity that helps us to define whether a flow is likely to be laminar or likely to be turbulent. And that's called the Reynolds number. And so the Reynolds number is a ratio of inertial terms on the top over viscous terms on the bottom. So mu down here is the dynamic viscosity. Rho is density. U is the velocity of the fluid. And L is a length scale. And the length scale could be something like the radius of a pipe or the diameter of a pipe, or it could be the depth of the fluid flow. And so those terms together give us the Reynolds number. And something that we do is actually combine the dynamic viscosity and the density over here into a single term on this side. I think I'll undo that so you can actually read it. And that we have as the letter nu. So this is nu, it's a Greek letter, it's not a V. Don't confuse it with velocity. Also, fortunately, we use U for velocity. So nu is just going to be equal to mu over rho. So dynamic viscosity over density. And so if the inertial terms are on the top and the viscous terms are on the bottom, what that means is that when the Reynolds number is large, the inertial terms will dominate and it will become turbulent. And indeed, for open channel flows, we often see turbulent flow when Reynolds numbers are greater than approximately 1,000. We see laminar flows when Reynolds number is less than approximately 500. So between those two, we have a flow that's classified as transitional. It's complicated. You have to think about the viscous terms and the turbulence, so the inertial terms all at once. And we're not going to do that in this class. But something I will bring up, and I have, I think, in a footnote down here, is that the Reynolds number is something that falls out of a non-dimensionalization of the Navier-Stokes equation, which is the core equation for fluid flow. And that's another important quality of it, right? So it's a dimensionless term, or dimensionless quantity. So the terms in the top in the numerator have the exact same units as the terms in the denominator. So I want to just have a few intuition building flows about whether something is laminar or turbulent. So one of these is, let's have something like a 1 centimeter thick layer of honey flowing down a ramp into the waiting mouth of a hungry bear. When I came up with this idea, I thought it was kind of cute, but then I realized now that I have to draw that. Don't have a brown. Let's make a black tree trunk. So we have this, some green leaves. And then we have our little ramp that the bear has set up that's going from the beehive down into the bear's waiting mouth. We're going to make it be an orange bear. So orange bear with a big ear on that side. Oh my gosh, this is going to look terrible. Hold on, let's try this again. All right, you know what? This is going to be Big Mouth Bear. I bet. Looks a little bit more like an orange alligator. All right, we're just going to write bear and switch to math. And I'm going to have to apologize to my middle school art teachers because I continue to fail them. Maybe it's a little bit more of like an bear, like an alligator bear combo. Well, so anyway, we have these terms, and I haven't done the math yet on this, and I'm going to do it in my head and kind of show you how I go about doing this because, you know, we all have calculators, computers, smartphones, whatever. But it's important to be able to do this sort of stuff just in your head, because then you can build some intuition and think through problems instead of constantly needing to throw it into a calculator in order to solve them for you. And it's just really good because you can make mistakes with calculators, but it's harder to make a mistake with your own brain, at least I've found. So if we have the Reynolds number, let's just go up and look at what it is one more time. So that is density times velocity times length over viscosity. So I'm actually going to write it in a little bit different form. I'll have velocity times length as one term, and then I'm going to have it as density over viscosity, just so I can lump these terms that go into nu together. So if we have this, so the thing that you do when you're trying to solve things in your head, you don't try to solve it all, you try to solve the simple problem first. And so the deal here is that we have to figure out whether it's like less than 500 or whether it's greater than 1,000. And so maybe kind of order of magnitude math is going to work pretty well. So we're just going to say that this velocity of the honey is, well, that's easy, 10 to the minus 2. The length is 10 to the minus 2. Great. The viscosity is 10 pascals, also easy. And the density, I'm just going to say this is approximately equal to 10 to the 3. Great. And so now what we have here is 10 to the minus 4 times 10 to the 3 over 10 to the 1. And so that is going to cancel this out and make this 10 to the 2. And so what we're going to end up with is approximately 10 to the minus 2. And then we can bring this, 50 back in and say, all right, we have actually 1.45 times 10 to the minus 2 equals Reynolds number. And so therefore, if we want to write it in non-scientific notation, Reynolds number equals 0.0145, and that is it. And this is very laminar. So our alligator, I can't even keep a straight face looking at that. Our owlbear is having a nice kind of smooth stream of honey entering its mouth. All right, so it's going to get worse. So a 1 centimeter thick layer of water flowing down a ramp into the waiting mouth of a thirsty hare. Well, fortunately, let's see. I think I might be able to get a little long-eared creature going. But let's say that this hare is kind of using a similar trick to the bear, and it has a tree, and there's some sort of invention that the hare has made so that, when rain is falling, it's able to tap, shake the tree a little bit, maybe by thumping its feet, bring some water down from the treetops on this ramp, and then, now let's make this hare. We have a big ear, big bunny ear, here on the inside, and then the hare's face is here, and it's, oh, okay, that's way better for now. It can still get worse. Let's see, we have the back of it, little fluffy tail, and the big thing I need to make sure that I get right are these gigantic feet with this big kind of muscly thing there, and it'll be a slightly plump hare. Oh wow, that's not great, but that's so much better than the bear. So, first off, density of water is 1,000 kilograms per meter squared. And so let's just write out our Reynolds number definition again. So Reynolds number is equal to velocity times length scale times density over dynamic viscosity. So right here, we have then velocity is 0.1 times length scale is 0.01, and so together this gives us 10 to the minus 3. Density is 10 to the 3, and then we have 10 to the minus 3 Pascal seconds down here for the, pardon me, for the viscosity, for the dynamic viscosity. So we have 10 to the minus 3 times 10 to the 3 over 10 to the minus 3. And so these two would really make this 10 to the 6, but it's nice and convenient. We can cancel out these two terms, and then we get the Reynolds number is equal to 1,000, right? 10 to the 3. And this classifies as turbulent, but barely. Right. And so this is dangerously close to these transitional flows that we think about. And so maybe it's going to be a little difficult for us to think about these really thin sheets of water because they might be laminar, they might be turbulent. So let's move to something like a 1 meter deep river flowing next to the bear and the hare. Oh no, I added those two again. All right, here. We're just going to do this in map view. And I'm going to draw some like grassy banks of the river. And we're going to have a nice little point bar on the inside of this bend here, filled with gravels and sands maybe. And then I'm going to draw in map view. Here's our hare. And there's a little fluffy tail. There's an ear. There's another ear. And then the next one is going to be our bear. Wow, I can't even write this. So there's our owlbear. And inside the channel, we have some sort of water flowing around. So the question then becomes, what is the state of this channel? And you might be able to intuit, based on the fact that it's flowing faster and it's deeper, that the Reynolds number just might be more on the turbulent side. Let's do this one more time. Reynolds number, velocity, length, density over dynamic viscosity. All right, so this one is the same as before. It's 10 to the 3 over 10 to the minus 3 equals 10 to the 6. These two over here then are 1 and 1. Well, that's easy. And so now the Reynolds number is equal to 10 to the 6 is equal to 1 million. And this, my friends, is a turbulent stream. And this is why, in geomorphology, we're going to be thinking primarily about turbulent flows, because natural rivers such as this are so far on the turbulent side of the Reynolds number that we don't have to think about laminar flows. Now, if you end up thinking about flow inside the Earth's mantle, flow of molasses across the street after a major molasses tanker accident, or something like flow of lava through lava tubes, although occasionally really hot lava can be turbulent, but let's say just nice, slow-moving kind of Pahoehoe style lava, then you might be thinking about laminar flow. But here we are thinking about fully turbulent flow, and that is our purview for the rest of the course.